Hi everyone, welcome back. I am Dr. Mohammad Uzair and today we are going to start a new topic. The new topic is the entropy. It is very necessary to understand the concept of entropy because entropy plays an important role in thermodynamics, especially in power generation. So what is entropy and from where the concept of entropy was established? So we have the second law of thermodynamics that you already studied in previous lectures. From the second law of thermodynamics, we know that there is no heat engine having 100% efficiency. So it's mean there is something that we are going to waste. So second law of thermodynamics basically leads to the definition of a new property called entropy. And entropy is a quantitative measure of microscopic disorder of a system. Or we can say that the entropy is the measure of energy that is no longer available to perform useful work within the current environment. So it means entropy is not good for any system, but still there is entropy. So entropy is the measure of energy that cannot be used. So how we can get the equation or the definition of entropy? So in order to find a relationship, we have to perform or we have to check the Clausius inequality. So let's suppose we have a system in which we have a reversible cyclic device like this one, and we have a piston cylinder device. Now this combined system, you can see the dotted line here. So this is basically the boundary of the system, combined system. So we have a system here and we have a cyclic device here. So this system is basically receiving the energy from a thermal reservoir, and the temperature of thermal reservoir is, let's suppose, PR, and the amount of heat that this system is going to take from the thermal reservoir is QR, and I'm writing N as a differential here because it's for path function or the delta function. So we are getting a small, an amount of QR from a thermal reservoir. This QR is shifted to this reversible cyclic device. This cyclic device is performing a work which is going out from the system, and the heat rejected from this reversible cyclic device is transferred to this piston cylinder device. Now this piston cylinder device is receiving the heat at a temperature of T, and the amount of heat that is receiving by this system is delta Q. Now this piston cylinder device is performing a work which is W system. So we have two work output. One is W reversible cyclic. So I'm just going to write the reversible here. So W reversible and W system, and we are getting an amount of heat from the thermal reservoir. So if I'm going to write down the energy equation for this system, this combined system, so I can say that the energy in minus energy out must be equal to the change in the energy of the combined system. This C is for combined system. And here we have the energy in, which is only the amount of heat that is coming into the system. So we have delta QR, then we have the negative sign, and then energy out. So the energy out from the system we have the work by the reversible cyclic device, and we have the work by this piston cylinder device. So the energy out will be equal to the delta of W reversible plus delta of W system, and then it will be equal to the delta or change of the change in the energy of the combined cycle or combined system. Here if you can see, we have only one input and we have two output. If I'm going to combine these two output, and I'm saying that we have WC, which is the work done by the combined system, then I can simply write down this equation by delta QR minus, instead of writing these two values, I can simply write that we have WC. So you can see here I'm just going to shift this whole term by delta WC, because WC is the combined work. So we have delta QR minus delta WC equal to change in the energy of the combined system. So this is the energy balance for our system. Now we have the energy balance for the combined system. We have the amount of heat that is coming into the system. We have the amount of work that is being out from the system, and we have the change in the energy of the system. Now let's suppose if we have the reversible cycle, reversible engine. So in the case of total reversible engine, we can easily write down that delta Q upon TR is equal to delta Q upon T. So it's simply, I'm just going back, so we have the relationship that this amount of heat that is coming to this system divided by this one, and the ratio will be the same as we are going to get from this one. If I'm going to divide this QR by this TR, and if I'm going to divide this Q by this T, so the ratio will be same for the total reversible cycle. So condition is the total reversible cycle, and what is total reversible cycle we have already discussed in the previous lecture. So for the total reversible cycle we have this relationship. So if we have this relationship, so I can simply rearrange the equation and I can get this relationship. So we have delta QR equal to PR times delta Q upon T. So I'm just going to replace this value by this one. So if I'm going to put this one here, so it will be TR delta Q upon T minus the change in the work, and it must be equal to change in the energy of the combined system. So the total net work done by the combined system becomes like this one. I've just rearranged the equation. So we have the net work done by the combined system, and it is equal to TR delta Q upon T minus the change in the energy of the combined system. Let's suppose we are going to check the total work done, and it will be equal to the cyclic integral of the incremental work. Right now we have the change and the work. So if I have to check the total work done, instead of using this delta, if I am going to check the total, so it's mean I have to integrate this one. I have to integrate this one. I have to integrate this one. So I have to integrate on both sides of this equation to get the total work done. Right now this is in terms of differential form, so it's mean we are going to check the incremental work done. So for the total I have to integrate this one. So if I'm going to integrate, so I will get like this. So we have the total work done, and it is equal to TR and integral of this one minus integral of this part. Now I have taken the TR as a constant value, because if you remember, TR is the temperature of the thermal reservoir, and normally we say that the thermal reservoir is a body having the constant temperature. If you are going to get the if you are going to extract the heat from the thermal reservoir, the temperature will remain constant. So it means that PR or the reservoir temperature is a constant value. So I have just taken out from this integral sign. And you can see this symbol here. So this is for cyclic integral. Cyclic integral means we are dealing with a cycle. So when we are talking about the cycle, so it's mean this value should be 0. So if the system as well as the heat engine is required to undergo a cycle, then there will be no change in the energy of the combined system. So the cyclic integral of the change of the energies of the combined system is equal to 0. So if this one is 0 for the cyclic integral, so I'll get only this value. So we have the WC, which is PR, the integral sign of delta Q upon T. So this is the total net work. So if we have this one, so the question is either this W is a positive one or negative, or the amount of the work is 0. If I'm saying that the WC is positive, if WC is positive, so we have a cyclic device which is exchanging the energy with a single heat reservoir. We have only thermal reservoir and we are getting the amount of heat from the thermal reservoir, and it is producing an equivalent amount of the work. So if I'm saying that the WC is positive, so it is basically going to violate the second law of thermodynamics, which is basically the Kelvin-Planck statement, because there should be a heat loss from the system. You cannot convert the complete heat into work. So if WC or the combined work is positive, so there will be only one single heat reservoir and we are going to produce the same or equivalent amount of work, which is not possible. So it means the combined work or WC should be either 0 or a negative value. So it means if WC is a 0 value, so it means there is no work done. So the engine as well as piston cylinder device is not performing any work done. Or in any case, if the WC is negative, so it means the work is done on the combined system. In these two cases, they are not going to violate the Kelvin-Planck statement. So it means if they are not going to violate the second law of thermodynamics, so I can say that this WC should be equal to either 0 or less than 0. So this WC should be equal to either 0 or less than 0. It cannot be greater than 0. If it is greater than 0, then it is going to violate the Kelvin-Planck's statement or the second law of thermodynamics. So if this one is 0, if this one is less than or equal to 0, and we know that this TR cannot be 0, because there should be a temperature or the absolute temperature should be greater than 0 for a thermal reservoir. So TR is greater than 0, so it means this value, this term is like this one. So we have this relationship. So we have the cyclic integral of delta Q upon T, and it is either equal to 0 or less than 0. So here this Q is the net heat added to the system, so I can rewrite this one by this one. So I'm just shifting this Q by Q net, because this is the net heat added to the system. There is no other heat transfer. So if we have the Q with this Q net, so we have the equation like this one. This equation is called the Clausius inequality. This is very important equation to define the entropy. So this one is the Clausius inequality. So this equality holds for the reversible process. So if I'm saying it's equal to 0, so it means we have the reversible process, and the inequality holds for the irreversible process. So we have the equality and inequality, normally we say that this one is the Cauchy's inequality equation. Let's say we have a question here. We have problem of 1. So here in this question, if you see, for a particular power plant, the heat added and rejected both occur at constant temperature and no other processes experience any heat transfer. So we have two heat transfer process. We have the heat addition and we have the heat rejection, and both processes are taking place at constant temperature. Now the heat is added in the amount of 3150 kilojoule at 440 degrees Celsius. So this is the amount of heat that is going in to the system, and then we have the rejected heat in the amount of 1950 kilojoule at 20 degrees Celsius. So we have the amount of Q and we have the temperature, corresponding temperature for both cases. We have two different parts. In the part 1 we have, is the Clausius inequality satisfied, and is the cycle reversible or irreversible. And in part B we have to calculate the network cycle efficiency and the Carnot efficiency based on TH and TL for this cycle. So in part 1 we have to check the Clausius inequality. And what is the Clausius inequality? We have simply the integral sign of delta Q upon T, and then we have this symbol either like it is equal or less than 0. But right now we have two processes, so it means we have to add the both process, and then we have to check that either the answer is less than or equal to 0. So how we can solve it? So the solution is here. So you can see here we have the integral sign of delta Q net upon T, and it is less than or equal to 0. Now because we have two processes, one is the heat addition process and the second one is the heat rejection process. So here I'm just going to replace this one by this one, just for in, and this one is for out. So we just written down the same values but with in and out, and then I'm saying that it is only for in. So we're talking about the heat addition, so I'm not going to put a cyclic integral, rather than a simple integral. So you can see there is no integral sign here. So, sorry, cyclic integral sign here. So we have only integral sign. So we have the integral of delta Q net upon T for inlet or the heat added, and then we have plus the integral sign of the delta Q net upon T for out or for heat rejection, and the summation should be equal to or less than 0. So when I'm saying it's integral, so in order to integrate, as it is mentioned that this T is constant for both, it is written in the question that the both processes are taking place at constant temperature. You can see here at constant temperature, so it's mean I can easily take out the T out from both integral sign, and then when I'm going to take the integral of this one, so it will be like this one, Q net, because this is delta Q, and then we will have the integral, so I'll get the Q here. So Q net upon T plus Q net upon T, this is for in and this is out, and then we have like this one. Now if I'm going to put the values, so we have Q net or Q in, so Q in is 3150 and T in is simply 440 plus 273. Remember that we have to put the temperature values in Kelvin or in absolute cycle. So we have 440 plus 273 and we have like this one. So we have 3150, which is the amount of heat that is going inside the system, and then we have this one 440 plus 273. So we have the temperature in Kelvin form. Then this plus, and then we have 1950, and this is the amount of heat that is going out from the system. That's why I'm going to put a negative sign here. Remember, in the entropy you have to put a positive and negative sign depending either the heat is going in or it is going out from the system. So this heat is basically heat rejected. So I'm just going to put a negative sign because it is going out. So we have 1950 divided by 20 plus 273 Kelvin. So when I'll solve this one, I will get the answer of minus 2.237. So you can see this one is minus. So it's mean this equation or this relationship is valid because the answer is less than 0. So it is less than 0. So if it is less than 0, so the Clausius inequality is satisfied. Since the inequality is less than 0, the cycle has at least one irreversible process. It has at least one irreversible process and this cycle is irreversible. If the value is 0, then it will be reversible cycle. But right now the value is less than 0, so it is irreversible. So in part B, we have to find the W net and the efficiency and the Carnot cycle efficiency. So what is W net? We have the basic definition that the W net or the work done is simply the amount of heat in minus amount of heat going out from the system. So simply we know what is the Q in and we know about the Q out values. So just you have to put the values and you will get the answer. So this is the amount of work that is done by the system. So we have positive one, so it's done by the system. So the efficiency is simply the thermal efficiency is simply W net upon Q in. We know what is the W net, which is here. We have 1200 kilojoules, so 1200 kilojoules divided by the Q in, which is 3150. So you will get 0.381 or 38.1%. So this is the efficiency, thermal efficiency. In the question, it is asked to find the Carnot efficiency as well. For the Carnot efficiency, we normally use the maximum and minimum temperature, and we have the Carnot formula, which is equal to 1 minus TL upon TH. So we know what is the TL. TL is already given, which is 20 degrees Celsius. So it will be 20 plus 273, and TH is simply 440. Then we have to add 273 in 440 to get the temperature in Kelvin. So by solving the formula, we will get 0.589 or 58.9%. So it is the thermal efficiency, but not thermal efficiency. So we have two different types of thermal efficiencies. One is the basic one, which is the thermodynamic efficiency, and the second one is the Carnot thermal efficiency. So the Carnot efficiency is more than the thermal efficiency of this cycle. And remember that the Carnot efficiency is the maximum one. No cycle has the efficiency greater than the Carnot efficiency. So this is the first question. We have another question here. And this question, if you see, almost we have the same problem. For a particular power plant, the heat added and rejected both occur at constant temperature. No other process experience any heat transfer. The heat is added in the amount of 3150 at 440 degrees Celsius, but the amount of heat rejected is 1294.46 at 20 degrees Celsius. So in this question, I have changed the amount of heat rejection from the system. So again, we have to find either the Clausius inequality satisfied or and is the cycle reversible or irreversible. And then in the second part, we have to calculate the work done and cycle efficiency for this cycle. The Carnot efficiency will be same as we have got in the previous question because the temperatures are same. So first of all, in part A, we have to check the Clausius inequality. So we are going to perform the same steps here as we did in the previous example. So you can see we have the integral sign of dq upon t, and it is less than or equal to 0. So I just replace in terms of in and out. So in and out. So in this case, when I'm going to put the values, so I have changed the amount of Q out. So when you will solve this one, you will get the 0 answer here. So you can see it's 4.418 minus 4.418. So you will get the 0. So it means we have this whole term equal to 0. So in any case, if we have the cyclic integral which is equal to 0, so it means the whole process or whole cycle is reversible. So you can see here the Cauchy inequality is satisfied. In the previous example, the Cauchy inequality was satisfied, but it was less than 0, so there was an irreversible cycle. But right now we are getting 0. Again, the Cauchy inequality is satisfied, but this time because we are getting 0, so it's mean the cycle is made of reversible processes. So all the processes are reversible. That's why we are getting 0 answer. So please be careful. I have just changed the values and you are getting the different answers. In both cases, we have in the first one, in the first question we had the irreversible cycle, and the second one we have the reversible cycle. So in part B, we have to find the W net. So if you can see, because we have the different value for the Q out, that's why we will get a different W net in this case, and that's why when we will put the values here, you will get the different efficiency, thermal efficiency. Last time it was around like 40, and right now we are getting around 50.9 or around 60%. So in this way we can check that either the system is reversible or irreversible. Up till now we have discussed about the Cauchy inequality. We didn't define the entropy yet. So how we can define the entropy? So for entropy, let's take another look at the quantity, this one. This is the Cauchy inequality. Now let's suppose if there is no irreversibility within the system, as well as we have the reversible cyclic device, then the cycle undergo by the combined system will be internally reversible. As such, it can be reversed. So if we have the reversible cycle or the internally reversible cycle, or there is no irreversibility, so if we have the internal reversible cycle, so what will happen? Normally for any reversible cycle we can say that for the reversible cycle we can say that all the quantities will have the same magnitude but the opposite sign. So in the reverse cycle case, all the quantities will have the same magnitude but the opposite sign. As we have already discussed that the work, which is WC or the combined work, cannot be a positive quantity, otherwise it will violate. Sorry, there was some noise. So if we have the WC with a positive value, so it will violate the second law of thermodynamics, as we have already discussed in the previous slide. And for the reversible cycle, as mentioned here, for the reversible cycle, there should be a negative work. But as we don't have the positive work, so we cannot have the negative quantity in the reverse cycle because the positive WC is not possible. So if positive answer is not possible, then we cannot get a negative answer as well in the reverse cycle. Because for any reverse cycle, we can get the quantities having the same magnitude but in the opposite sign because it's going to reverse by itself. So we can say that for the reversible cycle, the combined work of the internally reversible system is equal to 0. So it is not less than or equal to 0, it's simply equal to 0, since it cannot be a positive or negative quantity. And therefore we are going to replace this symbol by equal sign. So we are not saying that it's equal or less than or equal to 0. So simply we are saying that for the internally reversible system, we will have the integral sign of delta Q upon T equal to 0. So this one is for the internally reversible cycle. For internally reversible cycle, this whole term is equal to 0. So if it is equal to 0, so here we can conclude that the equality in the Clausius inequality holds for totally or just internally reversible cycles and the inequality for the irreversible one. So if we are going to get these Clausius inequality with equal sign equal to 0, so it means we have the internally irreversible cycle or total reversible cycle. But if we are going to get the answer which is less than 0, then it means we have inequality and we will have an irreversible cycle. So reversible and irreversible, please be careful with these terms. Now, to develop a relationship for the definition of entropy, let us examine the last equation more closely. If you see in the last equation, like here, so you can see we have the integral, cyclic integral of this one equal to 0. So we have the quantity whose cyclic integral is 0. Now, we know that the cyclic integral of work is not 0. Because if we have the cyclic integral of work equal to 0, so it is not a good thing, because otherwise you will not get a work from the power cycles or power plant. So the power plant will produce zero net work, because you are saying that there is no cyclic integral of work. So cyclic integral of work is not 0. Same way we can say that the cyclic integral of heat is not equal to 0. So we have work and heat, and the integrals, cyclic integral of work and heat, both are not equal to 0. So what are the things, or what are the properties that have the cyclic integral equal to 0? So let's say we have the volume, or we have the case here, we have pressure cylinder device here. So now consider the volume occupied by a gas in a pressure cylinder device undergoing a cycle as shown here. So we have a gas here. Right now we have a 1 meter cube, and it is going to expand, and then we will have a 3 meter cube, and then we are going to compress it. So it will, again we can get 1 meter cube. So in this case, we can say that is cyclic integral from here to here to here. The cyclic integral of this volume equal to 0. So explain the cyclic integral of a property is 0. So cyclic integral of a property is 0. So it's mean this one. So this one, delta Q upon net, and we will cyclic integral. And because it is equal to 0, so it's mean we have this one, and this is the property of the system. So this whole term is the property of the system. And this property is basically dependent on point. It is not dependent on path, because the cyclic integral of W, which is work, and the cyclic integral of heat, which is Q, both are not equal to 0. And right now we are getting this one equal to 0, so it means we have a property. So this whole term is basically a property. So a quantity of cyclic integral is 0 depends only on the state and not on the process path. Thus it is a property. So it is a property of the system. Therefore the quantity, this one which is like integral of delta Q net upon T in reversal, must be a property. So now we are going to define this one. This whole term is called entropy. It was discovered by the Clausius. So Clausius said that this whole term is a new property of the system, and it is called entropy. So since the quantity, this one, is independent of the path and must be a property, so we call this property the entropy. And normally we use word S to show the entropy. So S is designated for entropy. So we have the capital S for the entropy, and we have this small s for the specific entropy. For the S entropy, we have the unit of joule per Kelvin or kilojoule per Kelvin, and in the case of specific one, we will have the unit of kilojoule per kilogram Kelvin. So it is for specific one. So simply we can say that the entropy change during a reversible process. This reversible process, sometimes we can say that it is an internally reversible process. So the entropy change is defined as like this one. We have ds, the change in entropy, and it is equal to delta q net upon t for internally reversible. Or if we have to check the delta, or if I have to check the entropy change, so I have to integrate this one. So by integrating this one, you will get like this one. So you integrate between 1 and 2, and then we will get delta q net upon t for the internally reversible. Here we will get the s2 minus s1. So notice that we have actually defined the change in the entropy instead of entropy itself. So normally in thermodynamics, we are usually concerned with the change in the entropy. So we need the changes in the entropy of the system, rather than, we are not going to say that the entropy at point 1 or the entropy at point 2 is this one. Rather we will say that the entropy change between these two states are this one. So we have the entropy now. So there is a new property which is called entropy, and the formula for the entropy is simply S2 minus S1, and this is basically for the entropy change. So entropy change is simply integral of delta Q naught upon T. There's one special case, if the heat processes are taking place at constant temperature. So here we have a special case, internally reversible isothermal heat transfer process. Normally isothermal heat transfer processes are internally reversible. So whenever we have the isothermal heat transfer, then it will be an internally reversible system or the process. So therefore, I can simply say that this delta S is the integral of delta Q upon T, and because this T is constant, so I can simply take out from this integral sign. So I'm just going to replace this T by T naught, because I'm thinking that this T naught is a constant temperature of the system. So if I'm going to take this T naught outside from this integral sign, so it will be like this 1 upon T naught, and then I'll get this one, delta Q integral reversible between 1 to 2. So when I'm going to integrate this one, so I will get Q. So it will be delta S equal to Q upon T, where Q is the heat transfer for the internally reversible process. So we have delta S, which is delta Q upon T naught, because T naught is the constant temperature process, or the heat is transferred at isothermal process. So there is one more question here. If you can see, we have a crystal slurry device contains a liquid vapor mixture of water at 300 Kelvin during a constant pressure process. So we have constant pressure process. 750 kilojoule of the heat is transferred to the water. As a result, part of the liquid in the cylinder vaporizes. Determine the entropy change of the water during this process. Now if you can see, we have liquid vapor mixture. So for the liquid vapor mixture, we are going to vaporize some part of the liquid. So it means still we are in the phase change process. So in the phase change process, we have the constant pressure, so it means we will get the constant temperature as well. So for during the phase change process, we will get constant temperature as well if we have a constant pressure. So you have to find the entropy change of the water during this process. So it's very easy, because it is a constant temperature process. So you will get the equation like this one. We have the Q upon T of the system. So Q is given, which is 750 kilojoule of the heat is transferred to the water. So its heat is going to the water. So it's mean we have a positive sign here. So 750 upon 300 Kelvin. So you will get 2.5 kilojoule per Kelvin. So this is the entropy change. So this is the system. 750 kilojoule of the heat is going inside to the system. That's why the entropy change of this system is on the positive side of 2.5 kilojoule per Kelvin. In any case, if the heat is going out with the same amount, then it will be a negative sign here. So we can say that we will have minus of 2.5 kilojoule per Kelvin of entropy change of the system. So whenever the heat is transferred to the system, you will get a positive entropy change, and whenever there is a heat rejection, then you will get a negative entropy change of the system. So in this way, we have already defined the entropy. We will start the new section of this topic in the next class. For any question, you can contact me by email or by the message section. Thank you.